Hello and welcome to Microsoft Cloud for Public Sector Organizations. My name is Steve Plank. Everybody calls me Planky, and I'm a technology solutions professional in Microsoft concentrating on the Azure Cloud. So the content for this session is really simple. It's just three topics: agility at a price I can afford, the connected cow, which means absolutely not a thing to you right now, but it will do soon, and the transformation of the delivery of services to citizens. When you look at categorization of IT spending, there is an advantage to public sector organizations. Those organizations that are early on the adoption curve of new technologies get an advantage over those organizations that don't. And quite often, there's a little sort of minor competition between departments. Are you a leader or are you a follower? That kind of thing. But the main categorization to look at is what we call the window of differentiation is strategic IT, things which are going to make a big difference and are going to change the game. They're going to change the way that services are delivered in the future. And then there's the old stuff, which has been around for years and years and years, utility IT. It's your obligation. It's keeping the lights on. So when we look at what strategic apps need, they need the ability to support new modern business ideas, elastic resources. They need very rapid development because from an idea, the time from an idea to getting that idea into a production environment where citizens can actually use it needs to be as short as possible in order to get the best possible value out of the taxpayers' money. And then there's your obligation, which is just, what you really need there is low cost and reliability. This is the steady state, ongoing, day in, day out type of IT. So we think that the cloud can look after the window of differentiation for strategic IT and for your obligation with utility IT. It can look up after both of those models, those needs. When you look at organizational business patterns, you see these four patterns: on, off. So something like a school or a university or a college is an on-off type business. They have high levels of activity during the term time, and then during the holiday periods, almost nothing is happening. Very much an on-off business. And if you think about the provision of IT in those organizations, well, they will go away. They will buy a whole load of hardware and software to use. They will put it into data centers. They will look after it, nurture it. And most of the time, or a good chunk of the time, actually, in some educational establishments, it might be most of the time, it's not actually being used because there are no students there to use this. The next one you've got is growing fast, and the idea there is if you're a new department, if you're absolutely new department within an organization, or if you're just a completely newly created government department, you don't know whether you're going to be a massive success and the citizens, the public are going to use you massively very early on, or whether it's going to be a very slow burn. You don't really know what that's going to be. And so how do you provision the IT that you need? It's very difficult to make that prediction. The next one is predictable bursting. This is where you absolutely know there are certain times of the year that things are going to happen, and there are other times of the year when things aren't going to happen. If I think about, let's move away from public sector for a little while and talk about the fashion industry. Well, we know absolutely that there is going to be a big burst of activity at the beginning of the summer, the autumn, the winter, and the spring, because that's when the new collections come out. That's when the websites get busy. That's when everybody's logging on to find out what the latest fashions are. So they know that's going to happen. But there's also unpredictable bursting. There are times when things happen, especially in public sector, with things that happen in government. A new piece of legislation comes down and forces you to have to do something, and then that there's no way you could have predicted that in the future. A new government comes in, introduces a whole load of new initiatives that you have to just respond to. So that unpredictable bursting, that unpredictable um, set of business activity that you have to go through, which has to typically be supported by IT systems. So these are being able to respond to these kind of business patterns in quickly and at a price that you can afford. That's what organizational agility is. It's really easy to do this if you've got a huge bag of money, and it's no problem whatsoever to just line up thousands of servers to do these kinds of things. But when you've got a limited budget, that's when it becomes a bit more tricky and a bit more difficult. So if you look at this is a production environment. This is a typical production environment. It consists of an application which might be used by a department, consists of a web front end. You can three servers there, a couple of SQL servers, that's databases, a couple of Active Directories for usernames and passwords, and the business tiers, three of those. That's a total of 10 servers. 10 servers in order to provide that production application. And it looks as though that's where it stops, but it absolutely doesn't stop there. Because in order to get that into production, you will need over here. Look, I've got 3 developer workstations if you've got developers, or these could be management workstations for the people who are going to manage this infrastructure. There's a code management and build server here. There's a development server here. So this development server, what it will typically do is it will take lots of the componentry from the production environment. So, it's got the web front end, it's got a SQL server, it's got an Active Directory, it's got the business tier. It's all loaded onto that single server. And why is it doing that? Because you can't afford 10 of them. To try and get 10 servers for your development environment would be an overly expensive way of doing things. Okay, then you've got a QA environment, quality assurance environment, a UAT environment, user acceptance testing. There's a test server. So that the normal process is that you'll go from building something to managing it to development to test to QA to UAT and into the production environment. The test server will have multiples of these components on them. Interesting thing about dev and test servers is that, the web front end can always talk to the database on a dev server because it's sat on the same server. There's no network involved. There's no trickery involved. The Active Directory server in a test server can always talk to the business tier because they're both installed onto the same box. The difficulty comes when you try and separate these things into separate boxes as you would in production environments, which tend to be much bigger than the test and the development environments. So could we get rid of the development server and replace it with a full fidelity 10 server environment, which is an exact copy of what you've got in production? Well, the answer in most organizations is no, there isn't the budget to do that. Could we do the same thing with the test server? Could we get rid of the single test server and have 10 servers which are an exact copy of what's in production? Most organizations, the answer is no. There's absolutely nowhere near enough budget to do that kind of thing. Could we do that with QA? Could we do that with UAT? You can see why this doesn't happen. It's because the expense is absolutely enormous. But the trouble is, the types of problems that we catch quite often aren't caught until we get into the production environment when these things are spread across 10 different servers, which are in different network segments and different parts of the organization because of the way that the organization develops these things. And so quite often, a piece of functionality will go all the way through. It will go from dev to test to QA to UAT to post to pre-production to staging and then into production, and that's when the problem gets found. And then we're in a mad panic trying to go back to a previous version so that users can actually use the system to provide some business value to the organization. So we want to kind of avoid that type of thing. Okay, so when we look at the old world, the old way of doing things, what it really consisted of was one development server, one test server, 2 QA servers, 3 UAT servers, and 10 production servers. That's a total of 17 servers, and that would be what you would need to buy. You'd need to acquire that hardware, the software, the skills, the data center for it to go into, all of that kind of stuff. Now, what we're suggesting in this new world is that what you do is you buy 10 development servers. You buy a full copy, full fidelity, full copy of your production environment. You do the same for test. You do the same for QA. You do the same for user acceptance testing. You obviously do the same for production. That means you have to buy a total of 50 servers. That's 3 times as many. That's 3 times the cost. So here I am talking about the agility of being able to get things into production very quickly, to be able to respond to those business profiles we were talking about, like on-off processing, predictable bursting, unpredictable bursting, and growing fast. Being able to respond to those needs as quickly as possible, but it becomes almost impossible because the new world requires such a massive budget to be able to do that. Okay, so let's have a look at the way we would do this in the cloud. This is a price list for a type of machine called anything from a D1 through to a D5. You can see that here, look. There's the D1, there's the D5, version 2. And what you can see is something like a D3 V2 is a typical sort of server that you might find in a production environment. Has 4 cores, has 14 gigs of RAM, a 200 gig disk, and it's 26.2 pence per hour to run that. So let's think about all those environments that we had there earlier. The 50 server environment, 50 servers. I could buy 50 servers. I could buy a data center to put them into. I could buy all the racks. I could buy the software to install onto those servers, and I could manage and look after them and provide the electricity and the cooling and all the stuff that is required. Or I could run a D3 V2. I could run one of those servers for 26.2 pence per hour. Now, if I need 10 of them for a production environment, it's going to cost me 10 times that amount of money. So it's going to cost me, and if I run it for 8 hours, because that's the working day, it's going to cost me £20.96 per day to run a production environment. 26.2 pence times 2 hours, because when we're in our development environment, we probably only actually develop. We only need to deploy our code to the development server for a 2-hour window each day. Same with the test environment, same with QA, same with UAT. We don't need it to be running all day, every day, 24 hours a day, 24/7. It's not that kind of an operation. You run the test suite when you run the test suite. And if you run the test suite for 2 hours every day at 11 o'clock in the morning, that's what you do. So to get that to 26.2 pence times 2 hours multiplied by 10 servers is £5.24, and that would get you a dev environment. But then you'd need it's less than 10 minutes to provision this. You need 4 environments though, because you need a dev environment, a test environment, a QA environment, a UAT environment, and you in your own organizations might also have things like pre-production, staging, and so on. So you may have many more environments. So those additional 4 environments are going to cost another £20.96. And then if we look at the cost of storage, it will be it'll be less than £10 probably. If we look at the cost of data egress, we pay for the data that leaves these servers, that's going to be about £20. That will give you 300 gigabytes of data out of the cloud and into the users that are using these applications per day on your organization, in your organization. So that's £72 per day all up, which is not bad. And most organizations can afford £72 all up to provide that level of fidelity of a system which will allow them to completely develop their services in a way that is exactly the same as it is in the production environment. Let's have another look at this price list, because there's other hidden benefits in this as well. It's not just £72 a day to get that level of agility that we were talking about, but also if we have a look at this first server here, that's 1 core and 3.5 gigs of RAM. Look how much it costs, 6.6 pence an hour to run. Well, let's have a look. If you were to double the number of cores to 2 and double the RAM to 7 gigs, look what happened to the price. It doubles. If you were to double the number of cores to 4 and double the RAM to 14 gigs, look at what happens to the price. It doubles. If you double the power of the server, it doubles the price. If you double the power of the server again, so you're now on a 16-core server with 56 gigs of RAM, that's £1 and 4.8 pence per hour to run. That's interesting, isn't it? There's a linear relationship between the cost of the server and the power of that server. A server which is twice as powerful as a different server costs twice as much money. Why is that important? Well, because it means that 4 of those servers, 4 D3 V2s, costs the same, exactly the same, as 1 D5 V2, £1 and 4.8 pence per hour. So you can either have 4 small servers or 1 large server. Now let's look at the way that some people might think about provisioning a service. Let's imagine this is your public website, the website that is facing the public and they are going to use. So what you might do is you might say between noon one day and noon the next day is a 24-hour period. Let's put all of that on that one big powerful 16-core 56 gig server, costing us just over £1 an hour to run. Then we might say between noon and midnight, we'll run that on all 4 of, on that server. We'll run it on that server at just over £1. And then let's run it from 6 a.m. until noon. But let's not provide any service to the public at all between midnight and 6 a.m. because hardly any of the public uses the service there. Sometimes there's only one user on the service. Many times there's nobody whatsoever using the service. And what this means is that we can provide full service to our citizens between 6 a.m. and noon and midnight, and we can provide no service to citizens whatsoever between midnight and 6 a.m. and that's going to save us some money, isn't it? That's going to save us £1.48 an hour times 6 hours. However, let's just think about this. We said that 4 small servers is the same price as 1 big server. So another way of doing this would be to take 4 servers and provide all 4 of those servers providing that service between noon and 6 p.m. because we know that's a busy time of day. Let's imagine that the next thing is that we only need 2 servers between 6 p.m. and midnight because that's not quite such a busy time of day. Between midnight and 6 a.m. we only need 1 server, and then back the next day we're back to, let's just say that between 6 a.m. and noon we need 3 servers, and then looping right the way back to the next day again we can have 4 servers. So you can see here, rather than providing one big powerful server, either giving the service or not giving the service, we can tune it according to what the needs are. We know that it's really quiet between midnight and 6 a.m. So we only need to provide the service of one server. Probably nobody's using the system, but if 2 or 3 users do manage to get onto the system, then at least a service will be there. And that's the flexibility that the cloud is offering you. This is why we talk about agility at a price that you can afford, because these are all pennies per hour to provision these services. And you don't run them 24/7. It's a big mistake that many people make. They think that what you do is you go into the price list, you multiply each of these prices, the hourly price, by 24 hours, and you run your service 24 by 7 by 365. And as you can see in this diagram, there's absolutely no need to do that. You can run the service 24 hours a day, but you can provide different levels of responsiveness, because when you've only got 3 users on the system, one server is more than enough to service those users. Okay, it doesn't stop there. In your on-premises world, when you go out and you use your capital budget to buy a whole load of equipment and software and to run a data center, to put it into a building and all that kind of stuff, this is what you look after. You look at absolutely every item in the stack. This is where the value actually lies, and the rest of it is just a necessary evil. It's a captivating and fascinating evil. It's something which keeps us techies completely interested in what's going on. However, it is just a necessary evil. Now, when you use platform as a service cloud providers like Azure, then what happens is Microsoft, as the operator of the cloud, takes away a whole load of the responsibility for running that stack. So we will take away, you no longer have to crawl around underneath the floor reconnecting network cables. You no longer have to sort of look after storage arrays. You no longer have to take servers out of their racks and fix them, and take the dust out of the filters and all that kind of stuff and put them back in. That's all done by the cloud providers. That's not your responsibility anymore. If you also look at the data and the applications at the top, then that's really the application developer's responsibility. Now, that might be you. You might have developed the application yourself. But if it's a third party that's developed the application, they will write their own patches. You will have to apply the patches, but they will write the patches for their own applications. What this means is that you, as an operator of systems which you're buying in, commercial off-the-shelf systems and cloud-operated systems, you are only responsible for the runtime, the middleware, and the operating system. You have no responsibility for any of the other components. So that's another saving that you cannot get by operating a full stack environment, by buying hardware, software, a data center, and all the stuff that you need to run it. So that's one really big advantage that the cloud gives you. You can now start to see why you can really be agile now. You're only looking after 3 parts of the stack, and you can provide all of those services as we've previously talked about. Okay, it doesn't stop there though, because there is a type of service called platform as a service, and that's where we take away, the cloud operator takes away almost all of the responsibility that you have. If you write your own applications, you still have to fix your own bugs. If a third party writes your applications, they will fix the bugs and you still have to apply the patches to that. But you can see here you have no responsibility for running the runtime, the middleware, the operating system, virtualization, server storage, and networking. You can get an idea now of how agile that could make you. Okay, now we get into the problem always with public sector of OPEX versus CapEx, revenue budgets versus capital expenditure budgets. Let's just have a look at this. Let's take an organisation that invests £5 million in capital expenditure to be depreciated over a 5-year period. Let's have a look at what this looks at. There's a couple of things I want you to take notice of here. One is at the bottom of the slide here. EBITDA stands for earnings before interest, tax, depreciation, and amortization. Earnings is a bit of a misnomer there, really. It really should say expenditure before interest, tax, depreciation, and amortization. And EBIT is expenditure before interest and tax. So if we look at the free cash flow, then the capital expenditure for somebody who spends 5 million is -5. Things in brackets are minus. So -5 million pounds in the first year of capital expenditure. Then we get to the end of the year and we look at the balance sheet, and what we see is we've got an assets column, we've got an on-prem IT infrastructure. It cost us 5 million, but we depreciated it by 1 million over the first year, so we've got 4 million pounds worth of assets. As we come over here, we look at the EBITDA, the earnings before interest, tax, depreciation, and amortization is 0, and the depreciation is 1 million. We've lost 1 million. So we haven't got our expenses yet. We've lost 1 million. So the total, the EBIT figure, and this is a key measure of the fiscal performance of an organization, like a public sector organization. The EBIT number is a really important number. So the EBIT number here is -1. It's -1 million. So we spent 5 million. It's cost us 4 million. It's cost us 1 million to run it for 1 year. And after all the depreciation, the EBIT number is at 1 million. Let's now have a look at what happens if we don't buy any capital equipment. We spend £1 million on Azure instead of buying that equipment. What does it mean? At the end of the first year, we have no assets, which means we have no on-prem IT infrastructure, so that's 0. Our expenses were 1 million. We haven't depreciated anything, and so our total cost is 1 million. Let's go back to the previous slide. The EBIT was 1 million when we use capital expenditure. And then we go forward. The EBIT is 1 million when we use operational expenditure. There is no difference between the cost of running something as an operational expenditure or a capital expenditure. And I have a plea to anybody who's in a policy making position to be able to provide more operational expenditure to your IT teams so that they can take advantage of the modern way of doing IT, which is to use the cloud because of all those previous advantages which I've just told you, which are not available to anybody who's operating in the CapEx model. So that's why it's important. That's why it's important to understand it doesn't cost more money to run a system through operational expenditure. It does cost more money to run something through capital expenditure because you can't get the agility benefits that the cloud can give you in your own data center. Okay, this is a spreadsheet, which is this is a complex to use, but very interesting spreadsheet for you to go through what the cloud hardware and software lifecycle would be for putting stuff into the cloud. Now, if you want to get hold of this tool, you go to this location, go to aka.ms/Azure Impact, and you will find a white paper called The Total Economic Impact of Microsoft Azure IaaS. And that spreadsheet is part of the package, so you'll be able to use that to do some financial modeling yourself. Okay, we also use machine learning in Microsoft. What we do is we do a forecast which is based on each subsidiary around the world does its own forecast. The people in the corporation do their forecast. And then we use machine learning to learn about the way that our expenditure goes in order to provide another forecast, and that allows us to triangulate the 3 forecasts together. We like to see 3 numbers very similar, very close to each other. Ideally, they all add up to exactly the same figure. That obviously doesn't happen, but we see numbers which are very close to each other. The trouble is when you've only got 2 numbers and one of them was wildly different to another one, which one's right? So by providing machine learning, which is a higher order service from Azure, then we are able to triangulate this information to give us confidence that the numbers that we're producing are accurate numbers. Now this is a list of all of the services in Azure. There are 157 of them. 12 of them are infrastructure as a service services, as I showed you earlier, and the rest of them are platform as a service services. They're what we're really mostly what they are is a higher order services. But we like to talk about more than just that. And there's a few areas that I want to concentrate on. One of them is artificial intelligence, cognitive services, search, machine learning, Internet of Things, big data, and so on, business intelligence. And there's a couple of those that I would really like to concentrate on here, things like the bot framework, but they are machine learning and cognitive services. So let's dig a little deeper into these things. This is an example of a cognitive service which will work out how old somebody is. So if we go and let's have a look at this. Let's go search, and into the search box, let's search the internet for the Mona Lisa, and that's going to come up with some pictures. And then let's use that photo just there, that one. Click that, and it says this person is 24 years old, and that is roughly in line with what history thinks of the age of that person. I could use my own photo, so if I pick a picture of myself, that's me, and it reckons I'm 56. Now that picture was taken 2 years ago when I was 56. I'm 58 today. Now that's a cognitive service. That's an API. There's an API. Somebody wrote the website in order to capture this information, to capture the picture in the first place. But the cognitive service itself is the image. What we do is we pass the image over to the cognitive service. It does the estimation of how old I am and passes back the answer. And then somebody's just done a little bit of programming to put the number right smack in the forehead of the person who's having their age predicted. Okay, so these are the different APIs that are available. There's a computer vision API, there's a face API, that's the one which we just used. There's a custom speech, there's speaker recognition API, content moderator. So an API which will moderate content for you. There's language understanding. This is something which understands the different ways that people say things. So these are all APIs which are available. So rather than you having to write your own code, what you do is you write the simple interface, which interfaces between the user who's going to use the system and this set of APIs, and then you use these systems themselves. So an example would be this. This is Niels Bohr, and Niels Bohr said making predictions is very difficult, especially about the future. So what we've done to try and make predictions easier, especially about the future, is a thing called machine learning. So let's have a look at machine learning. This is a higher order service. This is more than just keeping the lights on. You know what I said earlier about the way that you provide services? There's utility IT, and that's what I've been talking about, the agility of utility IT. And now we're talking about higher order services, so making predictions using machine learning. So what we have is a scenario which consists of a common data set of 42,000 images of handwritten numbers. And what we're going to do is we're going to use machine learning to try and predict what the number is. So we have a CSV file. All these numbers have been digitized into 785 columns, a label, and 784 pixel colors. The label says what the number actually is. So a human has looked at this and worked out that that first row are all zeros, the next row are all ones, the next row are all twos. Even though if you look at some of those twos, they look a bit dodgy, don't they? They almost look like threes, or some of them look like and symbols. Okay, so we've got some digitized data. Here's an example of some digitized data. Each one of these squares that is empty contains the value 0, and depending on how much ink is in the other squares, depends on what the value is. So that's how we digitize that data. And we've got 42,000 rows of this information. There's a 3. Look, to give you an example of how we might digitize a 3. It's a handwritten 3. And then what we do is we're doing a machine learning experiment. So let me just show you how this works. What I have here, this is a video demonstration. So I'm going to create a brand new experiment, and I come into, these are all the different types of experiments I can create. There's lots of different ones. Let's just go to a blank experiment. I'll click OK for that, and it gives me a surface onto which I can build an experiment to do predictions of these numbers. So I've got a data set, and I've got my digit data. That's my digitized handwritten data. We can actually have a look at that data. So if I show you what the digitized data looks like, it's mostly zeros because, you know, those squares I showed you with the numbers in them earlier, they're all mostly empty, aren't they? So we've got the label there. That column is the label. Oh, I've got 785 columns, my apologies. You can see all these different columns here. Mostly they consist of the value 0. I'm only showing the first 99 columns. But if we go to round about this label here, this is the actual number which is handwritten. So you can see there's a 1, there's a handwritten, which we've told it the number is a 0, we've told it the number is a 1, we've told it the number is a 4, we've told it the number is a 0, a 0, a 7, and so on, all the way through for all of the numbers. So what we're going to do is we're going to teach the system how to recognize numbers because we've already shown it what some numbers look like. You can see there's some values in the middle here, mostly zeros as I mentioned earlier. Okay, so that's what the digitized data looks like. So now let's do something with this digitized data. So what I'm going to do is I'm going to split this data into data I'm going to use to train the mathematical model and data I'm going to use to check whether the mathematical model is right. So what I do is I simply drag over a split data box and I link them up. This is really quite straightforward, isn't it? This isn't programming. This is quite straightforward stuff to do. Okay, you can see here it says I'm going to take 0.5 of the data, half of the data as my training data, but I'm going to change that to 0.7. So 70% of the data that I've got, those 42,000 rows of data, I'm going to take that data and I'm going to do something with it. So let's just run through this and split the data. It takes a few moments for it to split. So we've now split the data. The next thing I want to do is to use a multi-class neural network, which is an algorithm. So I have many algorithms I can choose. I'm going to use a multi-class neural network on this split data to analyze it. And so what a classification of data means, breaking it into its classified parts. In this case, it's whether the number is a 0 or a 1 or a 2 or a 3 or a 4, etc. So what I'm going to do is I'm going to take the multi-class neural network and put it into my training model. I'm going to take 30% of my training data. Remember that modification I made earlier. And I'm going to use that to train my multi-class neural network and say, this is what a number 7 tends to look like. The data for a number 7 tends to look like this. And because I'm doing it with such an enormous number of rows, it will tend to get it right. It won't get it always right, but it will tend to get it right. So it knows I'm working on the label because that's the known data. So the next thing I'm going to do is I'm going to take the 70% of my data and I'm going to actually score the model. So I'm going to sort of see how accurate is this model? How many times does it get the answer right? So I've got this option here which says score the model. I'll take the trained model, and then I'll take the remaining 70% of my data and I'll run that through, because I know what the answer is for each of these numbers that we've got. We know what the number is. And so I can see whether I got it right or not. So that will score the model. And that will say things like, we reckon it's 98.7% likely to be a 7. We reckon it's 96.4% likely to be a 1, etc. Then I want to evaluate whether the model is good or not. And I have evaluate model, connect this up. You can see this is just a free flow, just a sort of a flow chart really, isn't it? And then I run this model and it's going to give me some answers. So it takes a little while for it to run through. And then what I can do is actually have a look at the results. So let's wait for it to finish. So now I can say, have a look at the evaluation results and visualize them. Now, what is it showing me? It's showing me that, let's have a look over here, that a 0, 98.3% of the time, it thinks a 0 is a 0. You can see here it says a 1, 98.3% of the time it thinks a 1 is a 1. You can see here a 4, 97% of the time it gets that right. Look at this one though, look. It says that a 5, 1.2% of the time it thinks that is a 3. Can you see at the top of the column? It says a 5, it thinks it's a 3 just there. And you can see why that is. Because a badly written 5 can look like a 3. Look at this one, look, a 3, 1.5% of the time, it's thinking that a 3 is a 2. Well, that's logical as well, because a badly written 2 can look like a 3 sometimes, or a badly written 3 can look like a 2. So we get not only the prediction, and you can see most of the predictions are up in the 90s, but we get a few of them, a few outliers where it doesn't give us great confidence. And that's because what we've done is we've taught the model how to recognize digitized data and what that data actually is. So that's what machine learning will do for you. We've taken a really simple example of just digitizing some handwritten digits and saying, what does that come out to? Now, what I can do with this is I can create an API. So that's what I'm doing now. I'm clicking the button to create an API, and that's going to go away, and it will make my model callable so that I can have an application which, let's just say I'm going to have an application which recognizes digits, and I can call that application. Now I think I need to move on from here. Let's do that. How do I do that? Go here. Okay, so there's my machine learning model. From that model, that runs on thousands of servers in the Azure data center. And then I have the ability to use my model and create a machine learning API. And then I can write an app that runs on thousands of servers. And I can write an application. In this case, I've got a phone application. I just simply draw onto it, and that will call my API. So if I make a change to my model, that will change the API, which will change the results that I get on all the mobile devices which are using the API. I've got a video here which describes how to use this this mobile application. It's just a demo application, but it shows you what's possible.
Okay, so I'm just going to draw some digits. I'll try a 7 and let's see if it gets it right. It says that's a 7. That's good. Let's try again. Let's try a 3. Do it again. And it says it's a 3. That's good. Should we try something? Let's try a French 7. 7. It's got that. Let's try a badly drawn 3. Something like that. Let's see what it thinks that is. It thinks that's a 2, and you can see why that is, because it's very badly drawn. It's supposed to be a 3, but it's a 2, and it's the kind of mistake that a human would make, isn't it? Let's try a 1. It thinks that's a 4. You see, so sometimes it's not going to be particularly brilliant. Let's try, what if we did that? Thinks that's a 5. So you get an idea of, you know, the accuracy of the prediction. It's going to get it mostly right, but there's going to be a few numbers that it's going to get wrong. Thanks.
Again, I think the important thing to model there, it isn't machine learning itself which has failed there, it's the model. So what I really should do is train that model more to recognize badly drawn 5s and badly drawn 1s, was it, or 4s? I can't remember, whatever it was. Okay, I want to talk now about the connected cow. So what happened was, you see these cows here, they have got on their legs a pedometer. And some Japanese farmers went to Fujitsu Systems in Japan and said, we want to have a more accurate way of predicting when we should inseminate the cows in order to grow the size of our herd. It's very important for dairy farmers to grow the size of the herd because that means they get more milk production. So they want to do two things. They want to grow the size of the herd and they want to get the milk to the public so that they can sell to the public. Now, what somebody noticed using machine learning algorithms was that cows move in a different way. So what they did was they got some scientists to say, you know, estrus, when a cow goes on heat, that's when it's the best time to inseminate the cow. But it only lasts for 12 to 18 hours, and it's every 21 days. So if you miss it, that means you've got to do it 21 days later. So that, you know, that can have quite an impact on the business. And the trouble is, for these farmers, this occurs mostly between 10 p.m. and 8 a.m. at night. And so how is it done today? How was it done before machine learning came along? Well, basically, farmers just look at cows and they say, I reckon that cow is in estrus now, and now would be the time to inseminate it. But it's just done through experience, the experience of years and years and years of looking after animals. So we're trying to provide a bit of scientific rigor here now. So what they did was they over here, you can see there's the pedometer on the cow, which communicates with an antenna, which talks to a receiver, which goes into a router, which routes all the way through to the internet and into the Microsoft Azure Cloud Center, where there is an Azure machine learning model there that looks at the movement of the cows. Now, if you look at the movement of a normal cow, this is the sort of thing you'll find. It's completely random. They move randomly around. Sometimes they move quickly. Sometimes they move slowly. Sometimes there's lots of steps. Sometimes there's only a few. But a cow that's going into estrus, well, that's the pattern that you get. And what we have discovered is that this is the start of estrus. And the ideal time to inseminate the cow is 16 hours later. That's the absolute optimum time for artificial insemination. But something that was extra discovered by machine learning was that if you do it in the early stages, you'll probably get a female. That's perfect for a dairy herd. If you do it in the late stages, you'll probably get a male, and that's perfect for the beef herd. So depending on whether you're producing milk or you're producing beef for consumption, machine learning can help you maximize the yield of the amount of milk that you sell or the amount of beef that you sell. So you can see how important. Who would have thought that something like farming and technology would come together to some greater good? So that's just giving you an example of how machine learning as a higher order service can be used to make predictions. In this case, it's predicting whether you're going to get a male or a female cow and when is the best time to inseminate the cow in order to get the result that you want. Okay. Poole NHS Trust, they are using machine learning in a different way. Let's just have a look at a video that they've produced to see how they use machine learning for epilepsy patients.
The neurology department at Hull Hospital provides services to the whole of the county. I was appointed as a consultant here. My brief was to set up an epilepsy service. The financial crisis meant that we didn't have anywhere near as much resource as we were originally promised, and that led to me starting to think about how we could change our whole process using technology to provide better care for patients with epilepsy.
We've been using the Microsoft Band with patients with epilepsy in the community, and we're using that band to track heart rate, skin conductance, movement, so we're measuring everything that's going on with the patients. Using machine learning, we know when patients are having an epileptic seizure.
If you imagine a patient who has a seizure at work and she's concerned about the possibility of having another seizure, if she goes with a wearable device and a phone, the wearable device might pick up that she is having a seizure in the device, sends a GPS alert to her next of kin contacts. You could send a notification to the hospital team who are looking after her seizures, and therefore we would make changes to her care. We could provide that advice directly back to her in real time.
We're trying to help patients understand themselves better, understand how to manage their condition better, and how to best use the health service in terms of its limited resources in keeping them well, as opposed to treating them once they've fallen off the cliff and become ill.
We think that there are around 8,000 patients with active epilepsy in Dorset, and we would expect around 4,000 of those to be seizure-free. We would hope that there'd be an additional 2,000 patients who we could potentially render seizure-free using these kind of technological solutions. So it potentially turns what can be a life-altering condition into a much more manageable condition long-term.
As soon as the programme came up, I had to be part of it. The one key thing for me is about being able to have that safety net, that support system, so that I can actually regain my independence, because what tends to happen, particularly if I'm out on my own, odds are I'm going to end up in the back of an ambulance or in an A&E. I hope to get better control of my seizures and ideally to get that life back that I used to have.
I do feel excited about the idea that we could do something which meets the needs of patients to actually improve their quality of life, to make differences to their life. It makes it interesting getting out of bed in the morning.
This is a great example of a new model of care, because we've got intense patient engagement, we've got different ways of working amongst the community nursing staff and the hospital staff, and it will ultimately help patients look after themselves better.
Okay, so the next question after that is whether your data is secure in the cloud. And rather than having me talk about the security of data in the cloud, I thought I'd run a video for you. So have a look at this. Okay, so we've now come to the end. So we had a look at 3 topics: agility at a price I can afford. You remember we talked about um, the types of systems that you could build with full fidelity test, dev, QA, UAT, pre-production, staging, those types of environments. And we talked about the different business models, things like on-off processing for educational establishments where they wouldn't need to pay for the IT resources that they would require in the non-term time. We talked about predictable bursting, where we know there's going to be some kind of a requirement for the business to use its IT resources, and we could predict when that is, and we could gear up for it in advance. Even unpredictable. And we talked about scaling the system. Rather than buying one large server and switching it on and off at the inconvenient times when users would want to use it, maybe we could use 4 servers and just have one server providing a quarter of the available service to the 2 or 3 users that might be using it right in the middle of the night. So this was all about being able to afford to be agile, to be able to deliver services to your public. We also talked about the connected cow, and the reason for doing that was just to give an idea of what machine learning could do for you as an example of one of the higher order services. And that would allow you to transform the delivery of services that you give to your public. I mean, if you think about what they are doing in NHS, in Poole NHS Trust with epilepsy patients, that is quite a transformational thing for those patients. You think that this relies on imagination. It's nothing to do with just installing the systems. It's to do with the imagination that you have for the types of services that you could provide, and then just acquiring those services from Microsoft and composing them into something which is useful to your citizens. Okay, hope that was interesting. Hope it was useful. Hope you found it good to listen to.